Okay, let's see if we can do this real quick. Minimum jumps to reach n via prime teleportation medium. You're given a number n length nums array. You have starting index 0, okay. Goal is reach the ending index. From any index I, you can maybe form one of the following. Adjacent, jump to index I plus 1 or I minus 1 if the index is within bounds, okay. Prime teleportation, if nums I is a prime number p, you may instantly jump to j not equal to I, such that nums at j mod p equals 0. If the value is prime, you may jump to another index that is a multiple of that value. Okay, so 1 goes adjacent to 2, 2 goes to 6 because the value 6 is a multiple of 2. Yeah, okay. So at most, okay, yeah, you can always use n or n minus 1 steps in order to just go from index 0 to n minus 1. Okay, so 2 goes to 3. 2 is prime. So I could go to 4. But okay, but probably the better way is 2 steps to 3. 3 goes to 9. 4 is not prime, so it goes to 6, which is not prime, which goes to 5, which goes to 8. Okay. Right. So the only things that you can jump is using primes. How big are these prime numbers? 10 to the 6th. 10 to the 6th. Okay, let me think. So you can go to prime, and then you can go to multiple to prime. Multiple of the prime. First off is, I keep on forgetting how to find primes. There's a faster way than just using division or using for loop. 10 to the 6th. That's going to be a lot of primes, I think. Let's look at the constraints here. 10 to the 5th. So it's not going to be n squared. It's going to be n log n. It could be dynamic programming, which might be, well, would it be dynamic programming? Maybe not. Seems a little, that seems a little unlikely. Dynamic programming generally has multiple dimensions, unless I can somehow make these things into dimensions. Would I be able to make them into some sort of dimension? Probably not. I wonder minimum number of steps. Minimum number of jumps. I wonder indeed. I wonder if I can somehow define the number of jumps from each, the minimum number of steps to each index, and then somehow push out that information into adjacent indices. So maybe if I look at the second example, so 2, 3, 4, 7, 9. So it's like I think of 2 as having 0 steps, 3 as having 1. But when I do 2, I would need to look at all the things that are multiple to 2 within an array and define those as also being 1 step away. But that's 4 is the only one. But for instance, if there's a 4, 7, 8, 10, is this all increasing? No, it's not all increasing. Then I would define like 4 as being 1 step away, 8 as being 1 step away, 10 as being 1 step away. If I could somehow do that, I'm not sure how I'd do that. How would I do that? It needs to be prime as the default. It has to be prime. So for each number that's afterwards, like 4, 8, 10, each of those numbers I need to do the prime factorization of it. And then see if the prime factorization of it, for every prime factor within the prime factorization, I would go to the number with the lowest step count. The number with the lowest step count, I think. Two to 4, 2 to 8, 2 to 10. I mean, what else could it, I mean, how would it work otherwise? If I see 2 is prime, I would need to go through the whole list of items after it to see if any of them match as a multiple of 2. That seems like an n squared process. Like, yeah, that seems n squared, which seems wrong. 2, 4, 8, 10. So I'm on a prime. 2 is a prime. 3 is a prime. Two is a prime, 3 is a prime. Two. So I'm thinking something weird can happen with like to get to multiple jumps. Like let's say What am I thinking of right now? Do I care about ever moving back? Not really. So it could be something like 2, 3. Let's say there was a 15 here. And then over here there's a 5. And then there's maybe 100. And then finally the answer is like the last number is 27. So you need to do 2, jump to 100. The 100 goes to 5, 5 jumps to 15. 15 goes, no, but then why would, okay, maybe there's a bunch of numbers in between here. Let's say it's a bunch of prime numbers, so like 11, 13, 23, 29, 31, something like that. So there's a bunch of prime numbers here. So 2 is going to skip all those numbers. So the fastest way is 2 to 5 to 100. No, 2 to 5, 5 to 15, 15 to 3, 3 to 27. So how do I do all these jumps? How do I do all these jumps? So 2, 11, I say 11 is 1 away, 13 is 2, 23 is 3, 29 is 4, 31 is 5, 3 is 6, 15 is 7, and then eventually I get to 100, which could be, let's say, 50 away, 5, which is 51 away. No, 100 would be 2 away. No, 100 would be 1 away because it's divisible by 2. And then 5 would be 3 away, or 2 away. And then that would make 15 3 away, and then we need to change 3. Oh, that's too bad. Why, that doesn't even make sense what the hell I'm trying to think about in terms of the process, and 2, that doesn't seem like it'd work. Oh my lord. Am I gonna get stumped by a medium? Fuck. Okay. How do... I kept a set of primes. I kept a set of primes or a hash map of primes and their index or their number of jumps. 100 would be 1 away. $100 would be 1 away. Would be 2 away. 100 would be 1 away. 5 would be 2 away. $100. How would I even make that fast? How would I make it fast? Two. So if I divided the numbers into composites and primes, or if I went through each number and basically did the prime factorization of each number, then I split it up into two sets. The set of prime numbers within the array, the set of composites, which all link to, for every composite, I map it to the set or the list of primes in its prime factorization. Okay, I can do that. That seems reasonable. Okay, so each number, put it in set of primes or composites. For each composite, find its set or list of primes in prime factorization. Okay, and then what? And then I need to actually start linking, putting jumps on these things. So I have a prime. Maybe I need to have a set of list of primes and the list of indices. List of indices of that composite. So if like there's a composite that is 100 multiple times in the array, then the indices where that 100 appears. And then I do the reverse. For each composite, for each composite, map to the indices of its, no, maybe for each prime, map to indices of composites where it occurs in the prime factorization. So for instance, if 100 has primes 2 and 5, then whatever index it is, 2 maps to that index and 5 maps to that index. So yeah, yeah, maybe. I guess it wouldn't be too much work. I think all these are, I'm actually not sure if find the prime factorization of all n numbers in the array is already too much work, but I think it's necessary. I don't see how you can avoid it. Well, maybe you can avoid it. I don't know. But anyways, if I could do 2 and then go from 2 to the list of indices where 2 would be a factor within the multiple 2, or I guess list of indices where the number is a multiple of 2. Then I can just say all those indices take one jump away. The question becomes like how I move from there. How would I move from there? I guess I probably use some sort of queue or stack. Probably do some sort of stack. The stack of indices that I'm dealing with. The stack of indices. That doesn't seem particularly fast, but at least it might work. Stack of indices. Yeah. Yeah. Okay. Okay. Stack of indices. So like each time I process the stack, I increment the current number of steps. Say I have a jumps counter. I guess the stack should start with index 0. And this is the process these indices, which all take current number of jumps. So index 0 starts at jump 0. I probably do need a scene. This can be false for n, and n is the length of the numbers array. Yeah, I need to do the prime set and the composites. So primes is just going to be a set, and the composites are going to be linked to the set of primes in the prime factorization. So I guess it should be a dictionary. And then I still need to do the reverse, like like maybe I'll call it prime lookup or prime linked, p-link, and that should be a dictionary as well. Maybe it's a default dictionary of sets. And this is going to be, the key is the prime, and the value is the set of indices of composites multiple of that prime. Okay. I think that's it. All right, so for jumps is 0. So for every value in nums, I need to figure out if it's a prime or a coprime, or it's a prime or composite. I think I need to use one of those algorithms. What is this? Fastest way to get prime factorization. It's a dictionary where keys are prime factors and values are their exponents. Factor ints returns a sorted list of unique prime factors. SymPy is within optimized trial division best for small numbers. 12 to 15 digits. A simple loop that checks square root n is often sufficient. You can speed up by removing all factors of 2 first and then incrementing your divisors. Skip. I wonder if I could do SymPy. So prime factors. Okay, I guess I'll test this out from SymPy. Import prime factors. SymPy. Okay, let's see. SymPy. Spell this. See if it works. Print prime factors of 1500. I think that's going to give me an error. I didn't close that while loop or that for loop. Yeah, SymPy is not within Leetcode. Okay. I think I need to just do, the other method, the square. This optimized trial division method. Yeah, trial division. So it has an empty array, divisible by 2, then just divide out all the 2's. Check odd divisors up to square root of n. Okay. Seems simple enough, even though I don't want to code this myself, to be honest. Okay, so this is Googled. Okay, anyways, let's go and just make sure that works correctly. Okay, 223555 is fine. Wonder how fast that is for resolving primes. So primes, they wouldn't do that. While D, it'd be checking. It would be checking every odd. It'd be checking every odd number up to the square root of n. So ooh boy. So it should. So this is O of square root of n, right? Is the speed at which this is the time complexity for this. So if there's n numbers, this be n square root n in terms of finding the prime factorization for every number. I guess that's still reasonable. It's slower than n log n, obviously. But n square root n is not impossible for 10 to the 5th being n. Okay, I guess that's fine. Okay, so so for every value in nums, if val not in primes and val not in comps, so it hasn't been done before, then I'm going to say factors is equal to trial division of this number, this value. And then if the length of factors is 1, then it's prime, right? Then primes dot add this value, else it's a composite, and so composite of this number is equal to these factors. I guess I don't need a default dictionary. Is it a set or a list? Is it a set or a list? Actually, I think I need to do the index root. So let's say k is equal k in range n. So this now index loop and value is equal to the nums at k. Maybe I don't want a default dictionary here. Oh, so it's a, never mind, it's just a dictionary. Yeah, I think this is fine. And then I also need to do the reverse linkage. So for every p factor, prime factor in factors, then the prime linked of this p factor adds this index. Okay. I think that's fine actually. Yeah, I think that's fine. So it has to be a prime in order for it to jump forward, right? To jump to another thing, it has to be a prime. Okay, yeah. Okay, so now it's actually to kind of solve it. So this thing should actually be before the stack stuff. So I'll move the stack stuff after. Do. So here I can say while stack. Actually, I don't want to have the next stack and the current stack, where the stack currently has everything that is in. The current stack has everything that is at one away, or the current. Maybe I should call this current. And then I should call. And then I should do something with the next stack. Or I can do a queue. I could do a queue. Maybe I can do a queue. So it'll be a double-ended queue, and then I'll have a current is, maybe a current size is 1. Alright, I think I need to take a break 1 second. Great, let's see what we got. Okay, so I think I had, yeah, I can do this in several ways, but I think maybe having a counter for the number of things in the current deck. And I guess it should probably be a for loop or while true loop. Might be a while true loop. So while true loop and then a for loop that goes through this current size of the deck and pops from the front. So for something in range size, then I'm going to take out the index, which is at the front. And then before I forget, so this is the end, this is outside that loop. It should be now size is equal to the length of the deck at the moment. So each time I process an index, it'll move back and forth to the kind of things that are one step away from it that hasn't been seen already. And then that adds to the deck at the back end. Adds the queue at the back end. And then pops from the front at the front end. Yeah. So like if the first index, like the number index 0, let's say it can move to the number index 2, and then maybe because that thing is also a prime number, it moves to all the multiples of that prime number later on. It'll push those other indices onto the queue to be processed when when it happens next. Actually, jumps should increment. So how do I want to do this here? I think I'll increment jumps now. Probably be more consistent if I did jumps as 1 here. Jumps equals 2, or plus equals 1 here, increments. If the index is equal to n minus 1, that's going to return this answer. And then I can do the side numbers. Yeah, I can do the side numbers. Let's see. I'm trying to think. Seen of -1 is true. I'm actually going to add this. No, this is wrong. Maybe I'm going to do something weird. I'm going to add seen pens a true. If if index -1 is, if seen is, if it hasn't been seen, then deck appends index -1. So this fixes the -1. And if it starts at index 0, then -1 is actually going to be something that's already seen at this point if I appended true. This is kind of hacky, but whatever. And then seen of index -1 is now true. If not seen of index +1, dec appends index plus 1, seeing if index plus 1 is now true. Okay, and then I'm going to do something like for every p-linked, prime linked, for, okay, actually, if, let's say I have value of this number, so value is nums at this index. If this value is in prime, and this value is also in p-linked, so if it's a prime number and that prime number is used as linkage to other numbers, then for every O index, other index in p-linked of this prime, if seen of O index is not true, if it hasn't been seen, then dec appends this O index, this other index, and seen of this other index is now true. I wonder if there's a way for me to like remove this thing. Like, can I remove this prime if the value is in prime and this? If the value is in prime, I think at this point I can actually do something like prime dot remove this value, because the first time I jump, so if the prime number is 2, right, then I would kind of move to everything that is a multiple of 2 in the array, and then I don't need to process any like future 2's again, so I can just remove 2 as being a prime number. I think that's fine. I think that's also a slight optimization. And I think that might be it, to be honest. It shouldn't really return -1 because there's always going to be a way to increment down to the end. Comp, oh, it's supposed to be composites. Should be with an S. Instead of prime. Always need to be careful about my pluralization. I like to have data structures that contain more than one thing to have it be a plural variable name. Like nums is numbers, primes for primes, jumps for jumps. Okay, am I off by 1? It looks like it does look that way. Why would this be off by 1? One, 2. So it starts with jumps is 1, and the dec is 0, and then adds 2. Right, or am I doing it wrong and I just am off by 1? I'm not sure why this is giving 3, to be honest. In my head, I'm thinking it should be 2. Alright, let me go ahead and print out what the deck is each time. The first one, it can only be it. So this is going to be 2. Is that not the answer? Why does it need to process 3? So the first step. Yeah, okay, yeah, that is incorrect, yeah. It is 0, so when I process 0, the number of jumps is 0, yeah. Whoops. Poor logic. I thought hard about it, and I really did when I first thought about whether or not it should be starting at 0 or not. And I still got it wrong. I did something to the judging algorithm, or the judging code, judging app. Yeah, it's too slow. Kind of surprised. Oh, just wrong answer. 757. So this never got there. So it's going infinite for it, almost certainly. 757. Huh. So 7 goes to the 5. 5 goes to the 7 for every value in primes and the values in p-linked. Y. So the deck originally has 0. And then this is not true, this is not true. So value's 5 or 7 here. So, oh shit. I think I need to say scene of the first index is true. I think. Wrong. Oh, 7 goes to 7 in one step. Right. 7 goes to 7 in one step. I see, I see. Because it's treating it as primes versus co-primes, but 7 is technically a prime. It's not. Interesting. That's really interesting. Okay. So for every, yeah, I see. I still need to have p-linked for everything, including co-primes and primes. Yeah. Okay, so I need to actually do this for everything. For every factor, p-link it. Yeah. Wonder if this fixes it already or if I still need to do some other fixes to this logic. For every value in primes and every value in p-linked. Well, p-linked here, for every value in primes, get the values in primes. And the values in p-linked. Well, this is always going to be true. Yeah. For every other index in the p-linked if it's not seen. Okay, I think this might be shucks. So it does 7, index 0. Let's go ahead and just print out the p-linked. Let me see what it has here for case 4. Yeah, so it doesn't have 7, 1, which is incorrect because the value is not in primes. Yeah, I see. If the value is not in primes, then do the prime factorization. I think maybe I need to not do this if statement. I think I need to do it with every single thing regardless. Is that right? It's not in primes and the value is not in composites. Actually, maybe I can say if the values, let's say stored is the prime factorization. Okay, so if the value is not in stored, then stored of the value equals the trial division. Well, actually, I guess maybe how do I want to do this? If the value is not in stored, then factors equals the trial division of the value, and then stored of this value is equal to its factors, else factors pulls from the stored of this value. Okay, I think that's fine. Okay, and then if the length is 1, it's a prime. I think I'm done with composites, I think. And then for every prime factor, I'm going to link this index to the set of indices that are linked to this prime factor. At that point, I'm done. Okay, there we go. Oh, somehow immediately knows. that's a solution. Not a very fast solution, but it's a solution. I wonder if there's something better than this for the prime factor, because I'm pretty sure that's the slow part. Okay, so set of primes, set of stored prime factorization, set of unique linkage for every value in the nums array. If it's not already stored, then find the prime factorization, otherwise pull it from the stored dictionary. If it is a prime number, add it. I might be able to put this into here. Like right here. If length of factors equals 1 prime, so I'll add this value. So I don't need to do it every single time. It's already been done. And then it does need to add this index to the list of index linked. That seems all fine. I guess it's kind of unoptimized in terms of how it searches. It's kind of unoptimized in how it searches. Not sure how you optimize it better though. For everything, for every index, pop left. If it's the answer index, return. Do the left side jump, do the right side jump if it's possible. And then for every if the value is in primes, so if it's a prime number, then every linked index to it, move to that index if it hasn't been seen, and make it seen. I think that's pretty fine, and then remove that prime number from the set of primes to consider moving on. Jumps, increments. Yeah. Yeah. I guess that's it. It's a slow answer, but I think that's just my solution. It's just slow. I don't see a big improvement. I think I'm missing something pretty big in terms of improvements. Looks like I'm off by an order of magnitude, which suggests that this is slow, I think. Because this is roughly O of n, I want to say. Maybe it's slower. Maybe I'm just not analyzing this speed correctly. All right. So the summary here, slow above solution is slow, but not really sure why or how to improve it. General idea is to decompose problem into some smaller pieces So one is to have kind of prime factorization, find prime factorization, either set or list for each unique value in array. That's my stored dictionary. Find set of primes in nums, and that's my prime set. Find or create kind of a hash map from primes to linked indices, or to indices of values multiple of it, or composites with that values multiple of it. Multiple of it. So that's going to be my p-linked default dictionary. That's the main one. This is the main one, as it'll be used to quickly identify from identify where the fastest route to the end is using, or it'll be used to identify what indices to move from current index, kind of one step away, one jump away, using the second action, using the second operation. Once the above is made, use a queue, a process queue, or some variant of that, such that you're processing a single index at a time, pushing adjacent or kind of teleportable steps to the process queue. Increment the operation counter once you finish processing every step at the current count. So the current count starts at 0 or 1, however you want to define it. You're processing index 0. You figure out all the indices that are one step away, one operation away from index 0, and you push that to the queue, increment the counter, and now process all those indices. All those indices have adjacent indices or teleportable indices that can go to one step away, and then you push all those ones to the queue. And then once you're done with that jump, obviously you want to break the queue or break the process queue once you're at the last index, or you can you have to do that. And then you also have a scene counter or scene array to prevent yourself from redoing indices. Also have a scene array or set to make sure to not redo indices. Have a break if have a return statement when at last index. Time complexity is going to be O of n squared n, since the prime factorization function that I used was O of square root of n. I'm pretty sure, I guess it's O square root of n, so I'm pretty sure that processing the Q takes that number, takes that time complexity as well. Since the Q does go through every index possibly, and then for every index it has to go through the number of primes at the index, or the linked primes at the index. I guess this might be maybe even slower than square root of n. It shouldn't be that much slower. I don't know. Space complexity, this should be O of space complexity, this should be O of n squared n, since each index might have square n factors, and you're storing that in your stored hash map. I'm storing that in my stored hash map here. Kind of sure.